It's a real pleasure to speak here on the Implementation Task Force report. On behalf of the Implementation Task Force team, it was a really big effort. I'm sure the team members are glad that this is coming to a conclusion. So let me get into it right away. The report is quite an extensive report, so I will show you a lot of information. I don't expect you to absorb everything, but this is on the record, so you can always look at it. So these are the pictures, the mock shots of the members of the Implementation Task Force. Okay, here we are. There were 12 of us, and we were very ably helped by 3 liaison physicists from the energy frontier and the theory frontier. The key question that we received from the Accelerator frontier to address was, what are the time and cost scales of the R&D and associated test facilities, as well as the time and cost scale of the facility? That's a simple statement, but it covers a lot. The report, or the ITF work and effort, built on the 2021 report, European Strategy for Particle Physics Accelerator R&D Roadmap. That was fortunate that we had this as a starting point. The charge for the task force was to develop metrics and processes to facilitate the evaluation of proposals and allow a fair, and fair is the key word here, comparison between them, including expected cost using the same or uniform accounting rules, also schedule and R&D status. Let's see. Okay, so we went through a process that I summarize here. In fact, we started in 2020 in preparation for a snowmass that would actually occur in 2021. So this is now almost 2 years. We met over Zoom every other week, and sometimes more frequently. It's actually more than 1.5 years. Early on, we decided that the task that we were given to look at all the accelerator proposals was really not manageable, and we limited ourselves to collider facilities only. So as required, we developed a set of metrics to evaluate the proposals and the concepts that we received. We did that in form of a spreadsheet with more than 60 entries, prescribed entries that we sent to all the proponents. There were 24 major collider proposals that were evaluated this way. We collected it from all of them. And as you can imagine, since this started about 1.5 years ago, a lot of things are happening in the meantime. So some of the parameters were changing, and we tried to accommodate as much as possible. In fact, I've seen some parameters changed even in the presentations this morning. So this might be an ongoing process. So I think it's converging. We held, earlier this year, we held Zoom meetings with all the proponents of these major proposals individually with the groups to discuss this process, the process we are undergoing. So they were clear what's happening, and they could give us input if they felt that things were not done properly or fairly, which we of course accommodated. And then finally, we gave all proponents an opportunity to fact check the draft report, and they could give us comments, which we also incorporated. I must say right here that ITF did not review the ultimate performance of the proposed facilities. That particularly is the projected peak luminosity of the facilities, but also power consumption, for example. That's something that was clearly beyond the scope of what we could do, and that's really a job for the community as a whole. But we focused on technical risk and R&D requirements, estimated cost, and plausible technically limited schedule. We formed within the task force 4 subcommittees that analyzed, evaluated, and compared the proposals with regard to physics, reach, and impact. And this is not actual physics. What this really means is the center of mass, energy, and luminosity reach of proposals. Technical risk, technical readiness, and validation. That was the second. Then size, complexity, power consumption, and environmental impact. And then finally, cost and schedule. And these subcommittees worked for the last year and a half. So what was our approach of evaluation? So to facilitate an evaluation that is most useful to this meeting and also hopefully to P5, the proposals were grouped into 4 categories addressing similar physics, plus an additional group consisting of collider versions that could be located at Fermi. So the 4 are Hicks Factory colliders with a typical center of mass energy of 250 GeV, high energy Lepton colliders that go up to 3 TeV center of mass energy, Lepton and Hadron colliders with 10 TeV or higher parton center of mass energy, then Lepton Hadron colliders, and then the 5th group, as I mentioned, is something that fits on the Fermilab side. We also decided to evaluate only 1 version per proponent proposals. They can't give us a set of versions and say, we want you to evaluate all of these plus upgrades. And so, no, we wanted only 1, but the proponents could select which one they wanted to be evaluated. In all tables and figures, we show luminosity per interaction region to facilitate comparing proposals with each other. For proposals with multiple IPs, we also list the total luminosity. We did not consider or include staging possibilities of different collider proposals, such as FCC-EE followed by FCC-HH. This would require that we somehow know or decide how the staging would proceed, and that we couldn't clearly do that. So it was only possible for us to treat each proposal as a standalone proposal. The only exceptions are Lepton Hadron colliders, that those proposals assume that there is already a Hadron-Hadron collider in place. Okay, and then with all this information and the 4 subcommittees doing their evaluation, we then prepared summary tables. So there are summary tables for each of these groups, and they have 4 columns with summary values for the 4 areas of valuations that I described earlier. So one is for technical risk and maturity. We list the years of pre-project R&D needed. This provides relevant and comparable measure of maturity and estimate of how much R&D is still needed before the project start. This includes feasibility R&D, R&D to get technologies to at least a TRL level of 4 to 5, that's it's sort of a working prototype, and R&D for cost and power consumption reduction. This last item doesn't directly affect risk, and so it most likely can actually be occurring in parallel with the rest of the R&D. Evaluating the risk of not achieving the ultimate luminosity goals by ITF was not feasible, as I mentioned before. However, performance risk is included as one of the technical risks in the technical risk subcommittee. Years until first physics, that basically is a measure for the schedule. This is the most useful item to compare scientific relevance of a proposal. It includes pre-project R&D, design, construction, and initial commissioning. Then project cost in 2021, $1 billion US. This is listed without contingency and without escalation, of course, it's in 2021 dollars. We used various models to estimate the cost, And we also collected cost estimates from the proponents, which are listed in the report. It uses known costs of existing installations wherever feasible, and reasonably expected cost for novel equipment. That's actually quite a challenging task. For future technologies, the cost estimate is quite conservative, and one should expect cost reductions from pre-project cost reduction R&D. And we used the same fixed bins for all proposals in the tables. And then finally, power consumption in megawatt as a measure of environmental impact. This includes all utilities. We used information from proponents, as I said, if provided, otherwise we made our own rough guess. But we did some believability checks on these numbers as well. Again, expect reduction from pre-project R&D to improve the energy efficiency, as well as develop more energy efficient concepts such as energy recovery technologies. Okay, so the first group was Hicks Factories. There were 10 that we have listed in this category. These are some of the layouts with their approximate size. And let me just go to the table. So in this table, you see those 4 columns I just described before, as well as center of mass energy, both a nominal energy that we used for the rest of the table entries, as well as ranges that are possible. And then peak luminosity in parentheses is total luminosity if there are multiple IPs. There are some footnotes here. Some facilities are optimized for 2 IPs. It would be different if you just had 1 IP. So that would affect these numbers a little bit. The energy calibration, in some energy calibration is possible to a very accurate level, the storage rings, and that's a real advantage. Whereas other facilities can collide polarized lepton beams, and that effectively gives them higher cross sections for certain processes. Again, that's potentially a significant advantage. So these are additional advantages that are not particularly listed in the table. And high energy lepton colliders, we had 8 proposals. So these are high energy versions of the linear colliders, muon collider, and the Wakefield accelerators, laser particle driven and structure Wakefield accelerators. And here's the table for them. The nominal energy for these is 3 TeV. So that's what determines the values in these columns there. Again, some allow for polarized leptons, which has an advantage. A lot of numbers, and this is all in the record. You can study it at leisure. Then the next group is high energy hadron colliders and lepton hadron colliders. 3 PP colliders and 3 lepton hadron colliders. And these are just the CERN and the Chinese version. And here are the main parameters of muon collider, Wakefield accelerators, and the hadron colliders. These are all the facilities that can go to center of mass energies higher than 10 TeV. The comments here again, polarized lepton beams have advantages. And of course, the parton center of mass energy for the hadron colliders is much lower than the hadron center of mass energy by about a factor of 10. And lepton colliders, their physics is actually quite different, so we really treat them in a separate group. There are 3 of them, LHEC, the FCC-EH, and then the Chinese version as well. And then finally, the versions that could fit on the Fermilab site, we received specific proposals for 4, sort of an ILC version, Helen, a circular collider, muon collider, and the PP collider. There is also a recent proposal of a CCC version that would fit on the Fermilab site. And in principle, other versions like CIRC or RELIC or other Wakefield accelerators, they could also be evaluated for siting at the Fermilab. Also, we didn't get a particular proposal, but that's maybe something that could be done in the future. Okay, and then we prepared summary plots, basically just to compare the luminosity energy reach of all of these different proposals. And so this is for the Hicks Factory summary plot. Again, it's luminosity per IP that's listed versus center of mass energy. So this is the peak luminosity here. And on this side is simply the integrated luminosity that you achieve in 10 to the 7 seconds or a snow mass year using these peak luminosity. Right? So there's a basically one-to-one correspondence of these 2 sides. Also shown are in these gray lines here, show the yearly production rates at these integrated luminosities for some important processes, right? So if you look here, for example, you can get many orders of magnitude more than 10 to the 9 Cs per year at the pole, right? So you can evaluate for each facility what their production rate is for any of these processes. So we have 2WW production, we have Higgs production here, which is centered here at 250 GeV, as well as TT bar production, right? Or double Higgs production. So you can see from this that if you reach up to 500 or 600 GeV in center of mass, you can reach these additional production levels, right? So you can see that the overall trend of the various types of facilities like storage rings drop off quite rapidly because of synchrotron radiation. The linear colliders slowly increase with energy and luminosity because the beams get smaller. And then you have up here, you have the ERL types, a circular ERL as well as 2 linear ERLs. Now, circular ERL can run at a higher rep rate than the storage ring, so it gives high luminosity, but eventually also have a problem with synchrotron radiation. The linear ones can always run at a higher rep rate, and so they can maintain a relatively high luminosity over a wide energy range. So that's sort of the 3 categories of types of colliders. The same plot for the higher energy, so continuing from 1 TeV to I think it's 15 TeV, or 20 TeV, yes. And so you could see the linear colliders continue up to about 3 TeV, as does the RELIC collider, the ERL linear collider. And then the Wakefield accelerators pick up there, go all the way up to 15 TeV, and the muon collider, of course, can also go up to about 14 TeV is what they prepared the parameters for. Again, there are lines of production as well as reach in discovery reach for the various colliders. And then finally, the Hadron colliders, they're sort of separate and quite different. It's a little difficult. It's difficult to put them on the previous graph. So here they are shown in terms of hadron luminosity, not central proton luminosity, but hadron luminosity. And which shows the high lumi LHC and then FCC8H and the Chinese SPPC as well. So the dashed curve represents the luminosity needed, assuming a 10-year run, to have linear increase of new physics mass reach with center of mass energy in this way. So you have more and more. The solid lines represent luminosity requirements for 70% of this new physics mass reach. So you get better and better as you go up in energy. Okay, so now I'm going to go through those subcommittees part of the report. There's a lot of detail here, so I may go through it rather quickly, but all the information is there. But let me go through this slide that may be a little slower, where the technical readiness of the collider proposal is being evaluated. So we developed metrics to compare the technical risk of key components and systems. Actually, proponents were asked to select 5 critically enabling technologies for their proposal and numerically evaluate each in 5 risk categories. So that's, again, a lot of information. One is the current technical readiness level of each of these 5 key components of critical enabling technologies. And they had to grade it between a basic principle observed, that's the lowest readiness level, to the highest one, being system proved through mission operation, that no critical technologies at that level. So that's the span from 1 to 8. That's called the TRL, technical readiness level. And then we further grouped it into just a score from 1 to 4. 1 least risky, 4 highest risk, right? Color-coded correspondingly. Then also technology validation requirement for this particular system, from a full-scale validation that represents a high risk, to separate component validation, just pieces, that's a much lower risk. Cost reduction impact, for example, from critical, basically a no-go without further cost reduction would just be way too expensive, to it's desirable to reduce the cost. Evaluation of performance achievability, from needs explicit demonstration to it's already at state of the art. And technically limited R&D timescale to reach a TRL of 7 to 8. Now that's further than initial pre-project R&D, but towards industrialization, from more than 20 years to 0 to 5 years. So these are the 5 categories. And that's the result that was received and evaluated, right, by the committee. This is for the Lepton colliders. And so you can see there are some things like ILC that has mostly light blue, no dark blue, and other things like particularly high energy CCC has some dark blue, and others have some dark blue like Relic. And so, so here you can see where the R&D requirements are for each of these proposals. Oops. And here's the same for PP, Hadron colliders, muon, and Wakefield accelerators. So there's a lot of dark blue here that needs a lot of R&D. And so this is the summary table that puts all of that together, as well as a maturity level. And the maturity level of design status maturity is categorized between TDR complete is the highest level, CDR complete, substantial documentation. 4 means limited documentation, and just parameter table. so that you could see that here, all the proposals were categorized like that. And then taking everything together, an overall risk tier was evaluated from 1 to 4. Lower overall technical risk to multiple technologies require further R&D. And you can see that here, and you can look at your favorite concept and see where it stands. And then finally, the question of how much will that cost? Now, that's a very difficult question to answer. But at the minimum, we assembled a list of past R&D efforts and how much they cost. Duration and integrated cost of the past, present, and proposed R&D programs. You can go through the list here. They're actually quite surprising. There were quite a few R&D efforts that produced demonstration facilities around the world, and at a substantial cost, right, sort of in the 100 million typically. And then set in here are all the demonstration facilities that are needed for all those proposals, with some estimate for the cost, not everywhere, but so you get a feel of what's really required overall. Again, sort of an eye chart, but you can always look it up later. And finally, power and complexity. That's the last subcommittee. So this summary table gives some numbers, summarizes the numbers for the various proposals in terms of power consumption, shown here. And with the color code, darkest blue is the highest consumption. Size, sort of linear extent. Complexity, that's sort of an overall complexity of how many systems are required. And also, if there is any radiation that needs to be mitigated, also indicated here. But this is basically just a summary table of the information that we were given by the proponents. Just want to make a note here. If you look carefully, you find that the Wakefield accelerators have a higher power consumption at 3 TeV than they do have at 15 TeV. You think, oh, how could that be? And we, of course, asked that to proponents too. How could that be? It turns out that at 15 TeV, unlike at 3 TeV, they would use round beam collisions. And so they can reduce the beam intensity to achieve the same luminosity and therefore have lower power consumption at 3 TeV. Okay. And then once you have luminosity and you have power consumption, you can look at the ratio and get sort of a figure of merit of luminosity per power consumption. And that's what this graph shows. It's luminosity per IP, as always, divided by the total power consumption of the facility. And there is an integrated version as well, integrated luminosity per terawatt hour. It's just the scale on that side. As I said, both luminosity and power consumption are really provided by the proponent. We did some check on the power consumption, but very rough. So these are the lines, and then the shaded areas are some judgment from ITF, how much higher the power consumption really could be than the maybe optimistic projection of the proponents. So you can see that shading area is below the curves typically. So that's sort of an uncertainty in this figure of merit as judged by ITF. And then cost. So estimated cost and cost uncertainties clearly are critical for project preparation, as well as for justification to funding agencies and society at large. Of course, it increases with size. The bigger the facility, the higher the cost, but not linearly. So it really needs to be looked at in more detail to understand it correctly. So what we addressed is total project cost. And as said, without contingency and escalation in 2021, $1 billion. This total project cost, which is sometimes called the US accounting, includes costs for all technical components, civil construction and utilities, all associated labor, that's often labor at the laboratories, in project R&D, not pre-project R&D, but in project R&D, design efforts, project management and other overhead, installation and initial commissioning. And then ITF prepared a 30-parameter cost model and benchmarked that model against 5 recently completed projects: XFEL, LHC, Swiss FEL, NSLS2, and LCLS2 plus HE. And it showed an error of less than 20%. So it's reasonably okay, the model. The 30 parameters that were used ranged from new and reused accelerators, tunnels and sources, operating power consumption, length and field of superconducting and normal conducting magnets, length of vacuum chambers, length and RF voltage of superconducting and copper cavities, number of beam dumps, number of cryo modules, cryo plants, plasma cells, drive lasers, to a 25% addition for design efforts and a 30% addition for controls, diagnostic cables, and installation. So that covers those 30 parameters, quite extensive and comprehensive. Then all colliders, except the Lepton Hadron colliders, were assumed to be standalone project. I already mentioned that, because we can't assume or decide on a sequence of projects. Lepton Hadron colliders did not follow that. They require the Hadron collider. Existing facilities like accelerators, tunnels, utilities that could be reused, of course, were not included in the cost estimate. Each collider was divided in a main collider and injector, power drivers, and sources. Cost of existing equipment, either off the shelf or from recent project experience, was used. And a model for the reduced cost for large quantity series production was also used. A range of cost estimates for novel technology, I already mentioned that was a difficult topic. The novel technologies identified for each proposal in the ITF report, so you can look up which technologies were considered novel, was obtained from a high value that's based on operating test facilities, and a low value based on reasonably anticipated advances and cost goals from current trends in similar novel technologies. For example, semiconductor development, you can see how the cost evolves over time. This was used here to get some reasonable estimate of how much the cost would come down in the future. But it turns out this evaluation has contributed the largest uncertainty in the cost estimate for future colliders. What's not included is cost reductions from future R&D. However, even though that could be quite substantial. Also, ITF followed the value plus explicit labor methodology. I sort of mentioned that a little bit before. So explicit labor is labor not included in the industry contracts, typically labor at laboratories. And the number that was used there was 200K per FTE year. Finally, the cost estimate was also compared to a simpler 3-parameter length, energy, power consumption model to get additional measure of the overall uncertainty. So that's all of it was quite an extensive effort. And that's the result of that effort. That's for the Hicks Factory proposals. This is sort of not quite linear or logarithmic cost scale up there. And the horizontal bars with the smeared ends indicate sort of the cost estimate range for each machine. So you can see it all hovers around $10 billion. Surprise, surprise. So a lot of work went into this and into these costs and the ranges. So they were they're quite meaningful, I would argue. And this is for the multi-TV Lepton colliders, both 3 TV and 15 TV. You can see the ranges here. And finally, the Hadron, Lepton Hadron Colliders and the Fermilab side filler. And some of them are outside the range. For example, this goes way below, way above 70 billion, I think. Okay, and I'm getting towards the end. The timeline analysis. So construction time of large project is determined by many aspects. There is a little graph of recent projects and their construction time. And you can see the red dots are European project, and they're sort of on a line here that sort of increases with cost, total cost. But the American ones just go straight up, seems to me. Just gets longer and longer. Anyway, so time to establish project and complete pre-project R&D is a factor, but a big factor is annual spending rate. And then as well as availability of experienced staff, big issue. And then civil construction often delays things, as well as fabrication of components. We, of course, could not include any of these because we don't know what that would be. So we focused on the technically limited schedule. We estimated timeline in 3 stages: basic design and pre-project R&D, TDR, technical design report and industrialization, and then construction period. Again, all projects are standalone, and the timeline starts now or when funding starts to be available, and it's technically limited. The years of pre-project R&D was informed by the technical risk evaluation, and time to first physics is not just the sum of these 3 stages, because some of it can go on in parallel. And so that's a table, again, an eye chart. But that's the numbers that were on the first summary tables came from these from this table. So a summary of the ITF judgment on collider projects on the duration, design, and industrialization, construction, and combined time to first physics. The first 3 columns, that's these 3, were the timescales as submitted by the proponents. And then these are the Hicks Factories, higher energy, and then the PP and EP colliders. Okay, it's my summary slide. So ITF developed metrics to evaluate and compare 24 future collider proposals in 4 areas: physics reach and impact, size, complexity, power consumption, and environmental impact, technical risk, technical readiness and validation, as well as cost and schedule, and produce summary tables and plots. And now some comments. Any of the future collider projects constitute one of, if not the largest science facility in particle physics. The cost, the required resources, and maybe most importantly, the environmental impact in the form of large energy consumption will approach or exceed the limit of affordability. ITF suggests that the SNOMAS CSS recommends that R&D to reduce the cost and the energy consumption of future collider project is given high priority. And then I'll put my other hat on as chair of the ICFA Sustainability Panel. I note that the 2021 European Strategy for Particle Physics Accelerator R&D Roadmap made this recommendation. Environmental sustainability should be treated as a primary consideration for future colliders, future facilities, including those in the near to medium future. And the R&D program should be prioritized accordingly. Objective metrics should be set down to allow appraisal of the impact of future facilities over their entire life cycle, including civil engineering aspects and of the resources needed to ensure sustainability. I think my main message here is R&D should be treated as a primary consideration for future colliders. SNOMAS should consider a similar recommendation. Thank you.
Questions?
Yes, in some cases, if you build a nuclear reactor next to a particle accelerator, you would say, and draw a circle about both, you could say you reduce the energy consumption and you raise the cost. Is this the right way to think about it?
I think that's not a bad way to do it, but I'm all for building nuclear reactors. No question.
Thomas, could you go back to the list of facilities that you've compared the cost model against? There is a list somewhere I forgot the slide.
I didn't quite understand what.
No, go back to the slide that contains the list of existing facilities that you compare the model, your model, cost model against. Okay, so these are the facilities. And no, you were on, go back to the previous, yeah.
I think your mask makes it very hard for me to understand what you're saying. Sorry.
Okay, could you please go to the slide that has the list of facilities that you compared your cost model against?
Oh, yep.
This one. Okay, so if I look at the list, the only facility here that would satisfy your criteria, which is brand new facility with no existing infrastructure built in the US, is on this list is NSLS2, which we know is a light source with quite conservative, no technical risk designs. It's a single data point essentially.
For the US?
But well, any other, we don't know the cost in the US, in your US accounting, because they're all European projects.
Yeah,
so
good point. Yeah.
So if I have to then judge about your error bars based on a single, very technically conservative, a single project, NSLS2, I mean, do I feel warm and fuzzy about it? I mean, I don't know what is the really truly cost model is benchmarked against PIP2, for example, which is, we know, 1.2 billion and 30 mega or 25 megawatts of power consumption. I mean, why PIP2 is not on this list, for example?
Okay, John isn't here, but I mean, PIP2 is not complete, for one.
Well, what we know, I mean, at least we know the cost estimate right now is pretty well defined, and the power consumption is well projected.
Yeah, I think fair thing to do. Maybe some other members have a comment.
So is John not here? So in absence of John Seaman, who led this effort, actually, we did get a conversion of a lot of these numbers. For example, the European XFEL. Reinhard Brinkmann converted that into a US costing model. Okay. Reinhard Brinkmann costed that in the US model. And Philippe Lembrun tried to cost the LHC in the US model. I have to confess, I forgot who actually translated the SwissFEL. But then we took NSLS2, LCLS2 HE, and subtracted off the tunnels and costed that again, and I think that was a reasonable comparison. So the 30 parameter model does include whether there's an existing tunnel or not an existing tunnel, and so I believe these were actually reasonable comparisons.
Maybe just a basic question of the site power. We're often looking at site power limit around 200 megawatts. And I wonder if these facilities costs are so large now that maybe it's $20 billion to build the facility. 200 megawatts is something like $100 million a year. It's just a small fraction. Why do we arrive at this certain site power limit? And why can't we push it higher?
But I think that's a good question, and it reflects, I think, the situation in the past. I think power consumption was purely considered a financial issue, right? And I think there is a change happening, that power consumption matters not just because of the cost, but simply because we have to reduce the amount of power we consume overall, right? Independent how much it costs, right? It's a sustainability issue, not a cost issue primarily anymore. I think that's a change. I think that was recognized by the European strategy roadmap. And I think it's also recognized by CERN, very much so, right? It turns out to be much more and more a cost issue as well, right? Because cost is going up, but I certainly think that's not the primary reason why we should conserve energy, right? Because we know use of energy creates CO2, right? Because we don't have enough carbon neutral energy sources, right? Yes, I'm for, let's build some nuclear power plants, right? But that's not the situation we're in right now, right? Energy is coming from coal and gas, right?
Okay. Heidi, are you there? Do you have a question?
Oh, sorry, that's left over from last session.
Oh, it's left over from last session. Okay. Somebody back up there.
So on slide 23, the one before, you said that there is an ITF. If you go to the slide before, which has a large answer. In the slide before, there's a large uncertainty band on the luminosity over power curves. Is that reflect, you said it's ITF judgment. What is the judgment based on the design status and risk or something else?
So it depends on various aspects. For example, here that's the relic facility, and the assumptions here for the power consumptions were quite optimistic, and we looked into that. In fact, outside person made it clear that we should look at that more carefully, and we did. And as a result of that, we added a significant amount of uncertainty. So it's different for different things, but for example, here, those storage rings, they have a rather small errors, right? So you can see the band is quite narrow. So it's not a precise number, but it's a judgment from the committee of the majority of the technology that's used to justify the lower power consumption.
If you can go to slide 31.
Did you say
31.
31?
So I'm, like you, very excited about the recommendation on the second bullet, but could you elaborate a little bit on what are the leading available R&D products that could be funded that have the potential to reduce the cost and energy consumption? And could you also comment on whether any of these R&D paths would have an effect on these particular colliders that are being evaluated for our short-term future?
Right. Okay, so in the past, I think the community was very successful in reducing power consumption very substantially by going to superconducting technology. Right? It's whether it's superconducting magnets or superconducting RF. Right? And there is a lot of additional R&D that can be done to further improve that. So superconducting technology is one area where power consumption.
Could you elaborate a little bit more? Because obviously we have superconducting technology now. So what kinds of improvements for?
One thing, for example, is the further development of the energy recovery technology, right? Using energy recovery Linux that can recover the beam energy and as such, that can be quite substantial. And in one of the options, the circ option, it allows one to reduce the synchrotron radiation in the concept. But I think also a very, potentially very significant power reduction can be obtained by improving the efficiency of cryogenic systems, of refrigerators. Helium refrigerators are extremely inefficient. Right? Not that it's very easy to improve, but they are inefficient. And so one could really make some progress in that area. But other energy recovery technologies like reusing process heat, right? All of these things can lead to power consumption reduction.
So this is Alain. Thank you, Thomas, for the nice talk. There was one thing which I was a bit surprised, and I would like to understand why you came to that conclusion. The FCC is presented as a series of machines, EE, PP, ions, EP, etc. And I found it difficult to understand why. This has been explained very well in the CDR and in the strategy. So why did you feel like not counting them together? Because it's a very important aspect of why it was chosen.
So you're talking about why we didn't look at a staging of FCC EE and then FCC HH?
Yeah, because that is very well explained in it.
Right, right. So we could do that, right? But then we would have had to consider other staging as well, right? For other machines.
Right.
And we didn't feel we should make that assumption or decide what kind of staging we should look at and what we shouldn't look at, right? So I don't think it doesn't preclude you from actually using this information for a staging like FCCEE and then FCCHH, because you can use the numbers and determine what the cost and the timeline schedule would be if you staged it, right? Right. So you could use this information to obtain a timeline for a staging, for example.
Yeah, but this has been done already. I mean, this is known information.
Right. And I think that the EF actually did just that, right? They used our numbers to make up a timeline for colliders. No, we need a microphone, I think.
Can you show the plot of this figure merit of luminosity per power consumption again? You made a remark that the error bar for the storage ring is small, but that's an illusion, right? Because you have to draw a vertical line at a fixed energy, and then the error bar is actually pretty big. We can allow for the error bar in horizontal direction because we need a Hicks factory. So I wonder why the error bar is so big actually for the storage ring.
This one?
Yeah. So if I draw a vertical line, then the width of the band is actually quite substantial.
Yeah, we can improve on that. I agree. Actually, yeah, it's not meant to give a large.
Yeah, it's not a small error bar actually.
Absolutely not.
It's a big one.
Yep.
Okay, so is Carrie DiPetrillo out there? Why don't you ask your question? It was in the Google Doc page.
So this is a highly naive question, and probably I could have gotten the answer.
Excuse me, could you start again? I couldn't.
Oh, sorry. My name is Carrie. I have a question regarding some of the tables on, I think it's slides 17 to 22, the color-coded tables. And so this is a very simple and naive question. I've never seen these tables before. it is very hard for me to process this sort of information, in a talk setting. I'm sure when I sit down and read the report, I can get it, but are there like clear takeaways, comparisons between similar types of machines that we can make? For instance,
I apologize, I have a very hard time understanding. If you could maybe lower the mask for asking the question.
okay, is this better?
Yes.
So are there comparisons or conclusions we can take away when considering similar colliders? For instance, for an E plus E minus Higgs factory, is there a clear winner in terms of low risk, low cost? Is there a conclusion that we can make from this study that can be summarized, in a couple of sentences for a non-expert audience?
Are you talking about this table in particular?
Not this specific one, but you had a series of tables.
Yeah.
Yeah, but is that just because more studies have been done, or is?
So
Okay. And then for
are you
the
asking?
similar question would be for a future high energy option. So deciding
Right.
between any sort of PP or high energy muon collider.
Are you asking whether one could draw a conclusion from this table which Higgs factory we should build?
Yes.
Okay. This is exactly what we try to avoid.
Okay.
But an important part of this table is this years of pre-project R&D, right? And you see there are two, a number that have 0 to 2. That basically says the project is ready to start, right? That's very important, of course. And so these are the first 4 here are in a position to basically, from a technical risk standpoint and maturity of the preparation, it's ready to start the project. Right? Not true for the others, but if that's the most important thing, then you would select one of those 4. Right? If your most important thing is lowest power consumption, you may have a different result, right? You would say, well, maybe I should pick this one here, right? Or this one. But that's can't be our judgment. That's the community judgment and P5, right? All we aimed to do was provide the information that you can make these kind of judgments.
Hello, Alexander from Fermilab. So all of these projects that you consider like, I'm here, like 20, 30 years assume 20 to 30 years of operation. When I consider going green with my house, the payout is like 10 years, and then I can sell basically electricity for profit. So from that point of view, I'm a little bit surprised you like so worried about power consumption, because over 30 years you will be able to build a green factory, green power plant, and take advantage of that, and it will save you money actually instead of wasting. And you don't have to build, say, if you speak about solar, you don't have to build it in Illinois. If you choose Fermilab to as a site, you can build it south, and because it's just huge power plant. So can you comment on why you don't consider this option? And then you are not limited in power, and it opens up your prospects in terms of using more mature and more accessible solutions.
Okay, so if there were plenty of carbon neutral energy source available in the world at this point, then that might be something to consider. But that's not where we are, and I doubt that we're going to be there anytime soon. and soon means in the next 50 years, right? So I think a reasonable assumption is that we need to always conserve energy on a worldwide level. Everything we do, right? We need to keep that in mind for everything we do. And it very much includes scientific facilities. Right? That's would be my answer.
Thomas, I mean, you did a phenomenal amount of work in here, and I think you communicated a lot of it. But one thing to emphasize that you stated up front is that we didn't evaluate feasibility of the projects. That was not one of the goals here. And we're using metrics to try and estimate costs, but that's basically using conventional accelerator technology, although the list of years of project R&D makes the assumption that there's some improvements. So for example, with the RE LC, there's an assumption that the Q of the cavity is improved by an order of magnitude. So, you know, if you can do that in 10 years, great. If not, then the power goes up. And that's, I think, one of the questions that was asked.
Right.
That was one of the questions that was being asked. And so the metrics that we have, and it's described in the report in some detail, but there's a lot of complication in here that it makes it hard to simply compare projects across without looking at, as you pointed out, the pre-project R&D or the timescale for first physics.
Right. Thank you, Tor.
So we need to get some people from Zoom in here. Scott, do you have a question?
Yeah, so to maybe ask the provocative question here, if we come out with a statement that power consumption is an essential factor in looking at any facility, and then we look at your nice colorful plot of cost specific luminosity, does that lead to the conclusion for funding agency that based on the SNOMAS recommendations, we put our money into structure Wakefield accelerators and RELIC, for instance, and if that means we have to wait for physics, we have to wait for physics under the assumption that every incremental watt's going to come from coal for the foreseeable future.
Okay, did I understand you correctly, Scott, that with a lot of emphasis on power consumption, maybe we should, that should determine the R&D that's being done?
I'm asking whether that is the statement that we're trying to make here. I'm not necessarily trying to push it one way or the other, but you put enough emphasis on the power consumption in our recommendations, and that's going to push very strongly towards saying wait for the physics and push hard on the technologies that have the highest performance per watt. I would think.
Right.
Do you agree, or I don't know?
Well, I mean, in the conclusion, we don't make recommendations, right? We just provide information to SNOMAS. We just suggested that one of the SNOMAS recommendation could be that cost reduction and electric power consumption reduction is R&D should be treated as R&D with high priority. Not at the exclusion of other R&D, of course, right? But just one recommendation. I think where the European roadmap went is that they basically said that sustainability R&D should be treated at the same level as performance R&D, right? It should, it should be treated as if it were a performance, right? And should not be treated as a second-class performance, as it has been now for forever, right? Didn't matter. Nobody cared, right, about that so far. I think that's the change that the European roadmap recommended, and we agree with that. Right.
Okay. We are getting questions from Google Doc, from Zoom, and from the audience. So out of the Google Doc, some questions were answered. The question number 4 from Kevin Pedro, I would like to give a little bit of relief to Thomas and ask Thor to answer that question. Question is, I'm glad to see the time to first physics metric given significant attention. However, the resolution on the values in the table seems unfortunately limited. It seems unlikely, for example, that all of the colliders listed as more than 25 years really have indistinguishable timelines. Is there any outlook for increasing the precision of these estimates in the near future? Thor.
Thank you for putting me on the spot, Vladimir. Look, we're, when you're talking about doing, looking 25 years out into the future, it's very hard to compare different projects. They all require substantial R&D, substantial advances in technology, and in many cases, even concepts. We don't have the physics concepts in hand yet. And so to try and really understand what the timeline is, I think is challenging. And of course, at the same level, understanding what the real cost will be is challenging. So you have to go with a certain set of assumptions, and then we put error bars on that as best we can. I hope that addresses the question.
Thank you.
Yes, I have a microphone. I would also, Gustav Boymans, Columbia. I would like to thank you for this amazing amount of work. There's a lot of information there, and it'll take some time to digest it all. It'd be even nicer if you could provide it in electronic form so people can make plots. I had a question about the interpretation about the years to first physics, because you have an R&D line and then years to first physics. So should I take years to first physics minus the years of pre-project R&D as a construction duration?
Yes.
So I can just take that. So if one thinks that, to take a crazy example, I don't want to make any recommendations like you, but to take an example of interpretation, if we say, look, around 2030, early 2030s, there's some free energy in the budget, right? So then we would be looking at starting construction on a machine in 5 to 10 years, right? And that means that effectively the machines for which R&D is between 0 and 10 years, or 5 years at least, are probably could all be considered on the same footing from a timeline point of view?
Mm-hmm.
Okay.
Yes, I think that's a very important conclusion, right? If funding is only available in 10 years, you want to do R&D to try and keep driving the cost down and the performance up during that time period. And for example, there's stuff like C-cubed, which has taken the normal conducting RF technology and has advanced it over what was done for click 10 years ago. And the same thing with this idea of the traveling wave superconducting concept, Helen, is taking the ILC technology, which was established 10 years ago, and advancing it. And you would want to do that. You would want to do that R&D if that's what you think your timescale for starting construction is 10 years or is 5-10 years from now. I hope that answers the question.
So first of all, thank you, Thomas, for a very comprehensive report. I think you guys have done a tremendous job. I guess my question is from the sustainability point of view, of course, power is a very important consideration, but I can imagine that there are also other components that go there. Like, for example, the size of the facility matters probably a lot as well as the materials that are being used, the amount of the certain materials that are being used, for example, use of helium for cryogenics, et cetera, et cetera. So I guess my question is there an attempt to somehow fold this into consideration? And I guess that would give some preference for compact facilities and the R&D for this, for development of these.
Spencer, please.
Oh.
Spencer, please answer this.
Okay, yeah, it's a good question. And in the environmental impact subcommittee, we looked at the size and power consumption. For example, civil engineering and like the removal of material has an environmental impact. We did not specifically look at use of helium and exactly how much helium would be needed. That was not one of our considerations. Other considerations were radiation dose based on beam power. So just some assumptions about energy stored in the beam and how much material would be generate, how much radioactive material would be generated. So those were the general considerations. They scaled with power and size of the facility, basically. One other quick point, there's been a lot of questions about power consumption, and in general, our statement is we want to reduce power consumption for the exact reasons that Thomas mentioned. In terms of green power, the cost of solar arrays have been coming down in California. So for example, $3,000 per kilowatt a decade ago, $1,500 per kilowatt now. So a gigawatt solar array, when we want to build this, would be about $1 billion, which might only be a 10th or a 20th the size of the machine. So we shouldn't rule that out. At the same time, we should aggressively pursue lower power usage.
Okay, we need to go back to Zoom. Steiner, are you there?
Yep. So that was a very useful introduction. Thanks, Thomas, for the nice report. I will continue on the same line as Spencer, in fact. So at CERN, we did a study of taking 10% of the construction cost of a future collider and put that into solar power and wind power. And then we look at how much of the running of the collider could come from such a facility. And it turns out we had a very conservative assumption. This was done for the linear colliders at CERN, 200 megawatt. Now we are down to 110. But even at 200 megawatt, we could run at 55% of the time fully on solar and wind power. And that's on 10% of the cost of the collider. So I think to rethink the way we finance these accelerators and maybe put some construction funds into providing power is a way forward. So this is in the same line as Spencer, and these costs are also coming down. That's a big advantage of this new energy source. Of course, Geneva is not the ideal place neither for sun or wind in practice, but maybe for other places, maybe even more relevant. Then I just wanted to make a pragmatic question to Thomas and company. We made some corrections to the first version of the report, and it would be very nice to see the second version of the report with the corrections in, because I see in some of these tables, I see some of the numbers are corrected and some of the numbers are not corrected. Nothing important, but since this report will be sitting around for quite some time, it'd be nice to have a check on version 2 of the report from the project point of view.
Yeah, actually, I think the snowmass meeting here is another round of fact checking really for the report. So we are really ask people to look at it, and if they see something that needs to be changed, let us know.
But yeah, my question was really, is there a second version of the report in the sense where you've already put in some changes, or should we work from the?
Right. Yeah, so we have to see whether we should distribute the most recent version. I think we probably should.
Yeah, I think that'd be very useful. It'd be easier for us to check then.
Right, right. And with regard to your first statement, I do agree that consideration of carbon neutral power for a new project makes sense. On the other hand, I must also say the cleanest energy is the one you don't use, right?
Yeah,
That's
no, no,
right. And so the first thing we should all do, and that is not just for facility, in everything we do, is do things more efficiently.
Yeah, that was not really the point of the comment. Obviously, the less power we have to deal with, the easier is also this way to mitigate the effect.
Okay, please go ahead.
Hi, yeah, this is Christian from Fermilab. I had a question maybe more on the technical side. I think looking at your numbers for the total costs, if anything, I might have seen that for all the cases, in the case of the muon collider, it came out a little bit to the left, maybe by a factor of 2 or 3 times.
Should I go to the cost tables or?
Yeah, the total project cost, I think is what you called it. And I wanted to see if there is a easy way to understand why that happens. Maybe here is the.
Is this the table you would like to look at?
I think if you look at all the 3 tables, I think it consistently to the left of all the other projects for maybe similar energies. So I wanted to understand if you could comment on why is that the case.
You're talking particularly about muon collider, or?
Well, like if I compare the ILC3 versus MC3, which I think it's maybe a reasonable comparison, I see like a factor of maybe, 50 or a factor of 2, 50% or 2.
I don't know. Vladimir, do you have an idea?
Actually, John Simon would be the best person to answer that. General understanding that first of all, yeah, you pay attention to the left-hand side, left-hand end of the bar, but also be aware that the right hand actually indicates the uncertainties. So within these uncertainties, usually colliders which are smaller in size require fewer elements like superconducting cavities or superconducting magnets look better. They're kind of shifted to the left. So muon collider is much smaller than FCCHH, for example, and that's reflected there. Plus tunnel size is significantly smaller, right? So a number of magnets required and so on and so forth. But there is a big uncertainty because it includes injector complex and so on and so forth, right? So yeah, again, the answer is extremely elaborated. So 30 parameters were taken into account to come with this number, right? So and the range again indicated there. But you see consistently that high energy colliders usually cost more. Shorter and smaller size colliders cost less. Colliders based on certain technologies are moved to the right. For example, not very certain technologies kind of usually show much broader range of cost estimates and so on and so forth. Yeah, the answer is not that simple, right? So again, that's the summary. And we have one question for Pushpa. And Steve, you tell us.
I just have a comment on the previous table. You had this first years to physics has caused confusion earlier. It doesn't take into account the real scheduling issues. For example, if CCEE won't be built until 2045 or 48 or something like that, mid 40s. So since that doesn't take into account real scheduling, maybe it should be made clear, right? Instead of just 13 to, I guess you want to keep this as is, I guess, that column, but you may want to have an asterisk and then have a footnote that this is starting from now. And I don't know if it's useful for the ones that are proposed, anticipated, time of operation, a year of operation or something. I don't know if you can add that information somehow.
Yeah. Yeah, there are a lot of caveats in this, that's for sure. So we try to keep it as simple as possible, right, without this table. But
yeah, but at least you could indicate that this is starting from now. It would
yeah,
be,
I think that'd be worth putting in the figure caption, in the table caption.
It's technically limited. That's what Tor is saying. Okay. Yeah, we have a time for one more question. Oh, two. Just a second.
Maybe a question and a remark. So I'm Frank Simon from Max Planck in Munich. On the sustainability discussion we had, I think it was previously already touched on the size of the facility. I mean, concrete is terrible in terms of CO2 footprint. And I think astronomy is starting to look into that. Is there any feeling like how would this, how important is the concrete of the construction compared to everything else? Has this been discussed?
It's good, very good point, but we did not consider concrete.
No, and then on this discussion that we had of building a power source together with a facility, I think here I agree with you. We have to be careful with this argument, right? Because this is publicly funded money. If we build the power source without the collider, we reduce the CO2 footprint further than building the power source and the collider, right? So this could backfire.
Right,
And I think we have to watch out for this.
Correct.
Fair.
Yep.
I think time's out.
Time is up. One more thing. I just want to thank Thomas for volunteering to take on this monumental task. I'm not sure he realized what was just, what it was involving. And the task force and all their hard work on this. It's been a
Can you stand
long
them
2
up?
years.
Guys, could you please stand up? Or stand up. Stand up. Okay. So the people on the front row, so come to them and ask them all kinds of questions about this report. Yeah.